Okay, why don't we get started? Hi, I'm Tony Stentz. I am presently courtesy faculty at the Robotics Institute here at CMU, longtime regular faculty and director of the National Robotics Engineering Center. I also did a stint with Uber on their self-driving vehicles and also Aurora with their self-driving trucks. This particular panel is going to focus on a series of projects that basically did off-road autonomy. I am going to focus on system aspects of that for the most part. Larry Matthies, who is also here from the Jet Propulsion Laboratory, also Carnegie Mellon, where he was a graduate student, will focus on passive sensing and perception. And then the other panelist is Jean Oh, who is on the CMU faculty presently, and she's going to go in a little different direction and going to talk about the interaction between people and the robots. Okay, let's get started. All right, so I like to think about the off-road autonomy problem as addressing a series of increasingly more complex scenarios. So when we first got started, we looked at the problem of just driving in a rigid world on flat terrain that had rocks, big obstacles sticking up, and following a sequence of waypoints that were pretty closely spaced. That was the first problem, and it looked an awful lot like the road following work that we were doing. So you basically try to follow a path, you see an obstacle, you stop for it, drive around it when you can. From there, we then relaxed the constraint that the terrain be flat and started to look at undulating terrain, terrain that had holes in it, that had steep slopes, that had cliffs, and now all of a sudden there were more types of hazards than just running into something. You could roll over, you could drop off a cliff, you could high center. And so that environment really, we ended up introducing this idea of doing feed-forward simulation, where you build a model of the environment, you, in faster than real time, simulate forward what might happen if you go a particular direction, and then pick a direction that minimizes the hazard or is most safe. We went from there to relaxing the constraint that everything be rigid in the world and started looking at compressible stuff, which was more often than not vegetation. And now we had to understand what we could crunch and drive over and what we had to actually drive around. And this is where we really started to introduce machine learning in a big way, because we had to understand, what are we looking at? And then finally, we went into very dense environments, and environments where you could easily get stuck, you could get lost, you have trouble finding your way to whatever the destination is, and that caused us to focus on things like how could we extend our field of view so we can see farther out, not get stuck, and we started to use maps in order to help us navigate, and we started to look at algorithms that would allow us to physically search and find our way through the environment. So that's kind of how things progressed from the standpoint of problem difficulty. Now, if you look at programs and platforms, there were a number of programs involved. In the 90s, there was the DARPA Demo 2, and a lot of the off-road autonomy was focused on the second vehicle in the series that Chuck showed, and that is NavLab 2, which was a military Humvee and able to drive over a little tougher terrain. And then around the turn of the millennium, a couple of programs were launched. The first was the Army Research Labs Robotics Collaborative Technology Alliance. And this was a massive program. There were 2 instantiations of it. Each one had an optional extension. It ran for 20 years. And it involved a whole bunch of players, including Carnegie Mellon, including Jet Propulsion Laboratory, and others. And we developed component technologies and integrated them on this platform here called the XUV at the prime contractors locale, which was General Dynamics. At the same time, DARPA launched a series of programs focused on structured and rigorous testing. in off-road environments. And the first one was Perceptor. It was perception for off-road navigation. And that was built around converted all-terrain vehicles. So you took a stock vehicle like a Polaris ATV and converted it to be an off-road vehicle. When that program ended, DARPA followed that with UPI, which was a awful acronym of acronyms, which stood for Unmanned Ground Combat Vehicle combined with Perceptor and integrated. And that was built around the platform that John Bears and his group built, which was Crusher, and going in much harder environments. So that's how things played out programmatically. If you look at all of these systems, the core piece is the local navigation system, and it was responsible for detecting obstacles, evaluating them, and finding a safe way to drive through the field of obstacles. We used an ensemble of sensors, cameras and laser radars and stereo vision, and it involved a classification step. So here's an example here. We had different classification schemes at different times. And so in this particular one, we're classifying the scene, finding the ground that could support the vehicle, and that's shown in red. The vegetation in green, and then the obstacles, which would be the front of the rocks, were shown in blue. This just shows a overhead view of the classification map. And then we would take the classified terrain, and we would look at how dense it was, how strong it might be. Because you can have something as vegetation, it could be very weak, like grass, or it could be very stout, like a dense bush. And we typically did that by looking at the LiDAR pixels and evaluate them in a three-dimensional voxel space and see how many penetrated the object versus reflected back. And by using this sort of density calculation, we would come up with a cost map for what we were looking at. And in this case, we're showing black means low cost, gray scales leading up to white or high cost, and pink meant lethal. Never drive over this. Now, of course, we drove over many lethal things, but we weren't supposed to. And once we had the cost map, then we would evaluate a family of trajectories driving over this terrain, evaluate how safe they were, and pick a particular one to drive. And the family that we would pick would be a function of how fast the vehicle was going. So slow driving all the way out to fast driving down here. So this is basically the way the system worked. And this simulation was faster than real-time forward simulation that was typically done 10 times a second. You drive a small part of the trajectory and repeat the whole process again. And this approach is still used in many, many navigation systems, both off-road and on-road. All right, so I promised Pete some perception stuff. So this is the yellow vehicle. So let me get that movie going. Yellow vehicle just driving on a trail through some woods. So you can get a sense of some of the places where we took these vehicles. And then on the right is a model for what the vehicle is using in order to navigate. This is the same trail, but the videos aren't synced. It has a little different color scheme. We never standardized color schemes. That was a mistake. The blue was low cost here, leading up through lighter blue to white being high cost, and then the red indicates very, very dense parts of the environment. And you can see we drive on the trail, which is easy to drive on, and you've got vegetation of differing costs that flank the trail on either side. Now, one of the problems with the navigation system is very myopic. Okay, so you're just seeing what's in front of you, and so if you have a complex environment, that a lot of times you could get stuck, and you'd have to back up or turn sharply. And so we were very interested in learning about the terrain well ahead of the ground vehicle. So in the Perceptor program, we proposed a flying eye, as we called it, which is one of Omid Amidi's helicopters with downward-looking sensors flying ahead of the UGV, detecting the holes, which are very hard to see from a ground vehicle, and other hazards, and detecting them, transmitting them back to the ATV, and then the ATV would plan a new path to get around the obstruction and direct the flying eye to fly along that path. So it was a very interesting interactive control problem. This is an early version of the ATVs. It was affectionately dubbed the Conestoga by DARPA. Here you see at the Buncher site, which has since been developed, you see the flying eye flying ahead of the Conestoga vehicle and detecting obstacles, transmitting them down, and the vehicle using them to navigate. We actually showed at Fort Polk that by having a helicopter flying ahead of you, you do reduce the time of the complexity of the traverse. Okay, in later programs, we didn't have a helicopter, but we were still interested in seeing farther ahead so we wouldn't get stuck as often. And so we started to ask the question, well, how can we make better use of the data far away from the onboard sensors? And the problem with looking far away is the pixels get spread out and they get really blurry, and it's hard to write algorithms to interpret what you're seeing at range. So what we noticed was, well, okay, so if you're at this point, P1, and you see something out here, a tree, you don't know how to interpret that data. But then as you drive forward and end up at P2, your local navigation system sees the tree, knows how to interpret it, assign it cost. You can treat that as ground truth and use that to train the perception system in order to correctly identify trees at a greater distance. And this was very effective. And we used this extensively through the UPI program. And this shows a traverse going from waypoint 0 through 1 through 2. The red is the traverse without the far-range online learning, which we called FROL. It includes lots of backups, which is what these kinks are. And then a little hard to see, maybe if you get the lights down, a little hard to see the cyan path, which is much smoother, which does not have the backups, that's making use of the longer range sensing. Possible to turn the lights off here? I don't know. Okay, we'll continue. I guess it's not possible. Thank you. This video here just shows a comparison side by side for a run of on the left, the far range online learning perception, and then the near range ground truth sensing on the right. So we were able to see significantly farther and make use of that in our runs. Okay. This when we did, and a little bit of sound here, DARPA took us out to places we'd never been before, typically military bases. And they put us on terrain that we didn't have a chance to practice on. So the idea was these were going to be true tests of how good our system was, not demos. And they would give us a series of waypoints that were typically 30, 40, maybe 50 meters apart, and we'd have to drive from one waypoint to the next. And they measured how long it took, how far we drove, and how many times the e-stop operator, right here, had to stop the vehicle to intervene and get it unstuck or prevent a hazard or prevent an accident from happening. So you can see some of these environments. They include some pretty dense wooded areas, and this is a marshy area at Fort Polk, and the vehicle has to figure out that it can drive over this grass, but some of these larger things it needs to avoid. We did the Perceptor program. It started abysmally for us. We did not perform very well, but it was a competitive program with multiple phases and down selects, and we made it all the way through the program, and we're the only team to make it through all of the phases. So it started poorly for us and ended very well for us. And I just want to mention Pete Rander was one of the leaders of the Perceptor program, and he is here with us. Okay. It wasn't all good. So this is an example of a run from Yuma, Arizona. And here the yellow vehicle is trying to skirt the edge of a cliff in order to get to a waypoint. And that's Eric Kratzer on the e-stop in the foreground. And Eric goes to get into position to get a better view of what's happening. Gets into position, and oh no, he raises his hand calling for divine intervention, does not get it, and the vehicle rolls over, crunching the sensors on the top of it. We were all located farther away from the robot in a room called the analysis room, and we're watching stuff like what you see on the right. You can see the video feed from the cameras, and look at the lower one. It's looking back at the e-stop operator. And we're watching all of this, and all of a sudden, whoa, what's going on? And that's actually the roll sensor, I think right here, that rolls all the way over. I remember turning to Pete and saying, something bad just happened. So we had stuff like that happen even later on when we were performing well generally. Okay, on to UPI. So this is when we switched to the larger vehicle, the crusher vehicle, I think 5 tons or so, a massive vehicle, and we said, oh, this is going to be great. Nothing's an obstacle for this vehicle, so perception and planning is going to be really easy. But DARPA anticipated that, and they decided to take us to some really bad places, okay, that had lots of vegetation, giant trees, giant rocks, giant slopes, basically nullifying the advantage of having this big vehicle. You can see some of the terrain we drove through. Again, we had laser rangefinders, we had cameras. There were a couple of chase vehicles. Sometimes this vehicle went into places that were so dense it was difficult for the chase vehicles to follow it. You'll see that at the end of this particular video. But we ran similar tests, and this is Fort Carson, Colorado, an aerial view. And this is a particular test where you had to go from a point here to a point here to a point over here and back. The waypoints were much farther apart, typically 1.5 kilometers apart or so. Here you can see the vehicle going through the brush, and the Humvees are trying to keep up. It's daylight again. Okay. Oh, okay. All right. Okay, and so you can see that there were some very, very dense environments that we drove through with these tests. Now, one of the things that UPI extensively explored was the use of maps, and we had a DTED map, digital terrain elevation data map, low resolution, high resolution map, and we would do runs where we would run without a map and compare it to runs where we would run with a map. And this shows at Fort Carson a run without a map. You're actually seeing the overhead data, but the robot does not have access to this data that you're looking at. It's just trying to go from a waypoint at the bottom to a waypoint at the top. And as it sees things, it classifies the costs. Again, black is low cost, white is high cost. And yellow is the path where it's been. Cyan is the path it has just calculated based on sensor data. And the purple, or whatever that is, pink at the top, that's a straight line, is the remaining path that takes you directly to the next waypoint. And so you can see it makes its way along here. There are places where it stops, has to back up, has to turn, gets stuck, has to get unstuck. But does make it to the waypoint, and DARPA would, again, measure everything: the time it took, the distance it went, and the number of times it had to intervene. So if you take a look at, you want to take a look at that run and compare it to this run. This one uses high resolution DTED data, level 5, which is sub-meter data, and that's the path in pink that was taken by the vehicle without a map, and now we will overlay that with the new path taken with the high resolution data. And you can see as the vehicle drives, it updates the map, it replans what it's going to do. You can see the pink path next to it has a lot of kinks in it where the robot got stuck, had to back up, go a different way, and this particular path is a lot smoother. Gets there faster with less trouble typically. So the UPI program ran for about 5 years, and over the course of the program, we drove over 1,000 kilometers autonomously. And by the end of the program, we were driving with about one intervention about every 20 kilometers through some very, very difficult terrain. Okay, there was also the RCTA program. That Jean's going to talk more about this, and Larry more about this. But we did develop a number of component technologies that were integrated on these other platforms, like Field D-Star, to give us smooth paths. We looked at how to navigate when you don't have GPS all the time, how you plan when you actually have probability models for the difficulty of the terrain. We also looked at how you might plan to coordinate a group of robots. In this case, these are robots that are trying to drive from one location to another, maintaining line of sight with each other so they could communicate. And you can see the path that they're taking on the far right. So this is work done by many, many people, people like Max Lukachev, who is here, and Juan Pablo Gonzalez, and Dave Ferguson. Many, many people worked on these component technologies, many of which were integrated into these off-road systems. I'd like to wrap up with just a couple of team photos. Many people worked on these programs, I grabbed a couple of pictures that show some, but not all of them. This is, I think, a pretty complete Perceptor picture taken from our Yuma, Arizona tests. And this is a picture of many of the people who worked on the UPI project. And just want to point out a couple of them. Tom Pilarski right here and Cliff Olmsted behind him, who were big contributors to all of this and unfortunately have passed away, and we continue to miss them. So again, many people worked on these programs. I think it advanced the off-road technology very significantly. Thank you.
Thank you. So I'm Larry Matthies. I finished at CMU in about '89, and I went to JPL. I'm still there. For 25 or 30 years, my niche was vision systems for off-road and other kinds of vehicles. These days, I'm the Mars Technology Coordinator. So one of the things that was fun, of the many things that were fun about these programs, is the great swag they gave us. So can you believe that 30 years later, I still have my Demo 2 hat and my Demo 3 hat? So enough of that. All right, so like I said, my niche in those days was mostly vision for off-road navigation. We had a significant breakthrough in stereo vision for off-road driving in the Mars Rover program, which we carried over into DoD, and JPL being a powerhouse in remote sensing all across the electromagnetic spectrum. I decided to see what I could learn from that and bring into the off-road driving world for DoD. So I'll talk about some highlights in the evolution of stereo for day-night 3D perception and exploring sensor phenomenology for off-road terrain classification. So it started with Mars Rover work. This is Robbie the rover. For scale, it's about 15 feet long. Our first real-time, called it real-time, it was kind of slow by today's standards, stereo vision system was a whole VME rack full of boards. For those of you who don't know VME, you know, it's boxed like this, you know, amazing compared to what we can do now. And we did the first autonomous off-road cross-country navigation demo in 1990, drove 100 meters in this dry river wash next to JPL, but it was only 3D perception. And if you're going to drive off-road on Earth, you've got to understand the terrain. Tony and everybody who spoke before me talked about that a lot. So you got to understand the vegetation and what you can drive through and what you can't. There may be obstacles obscured by the vegetation. Can you detect those or not? There's other stuff out there, like bodies of water, that you might like to understand so you don't plow through them faster than you really want to go. And then these holes in the ground, which we came to call negative obstacles in this business, which if you happen to get a chance to see them lengthwise, they're really easy to see, but if you're coming at them from the other direction, they're almost impossible to see. So Tony's group approached that by having an aerial vehicle out scouting ahead. We were thinking about, is there any sensor phenomenology on board that can help us with this? And just for fun, here was one of the more iconic watering holes that we stumbled across somewhere along the way up in the mountains in Colorado. There's Dave Hanholt and I at the Bucksnort Saloon, and there's Todd Yoakum. So unfortunately, I think he already left. Okay, so This was our first real-time stereo demo. In this depth map, dark is close and bright is farther, and we were only doing 60 by 64 pixels, 2 seconds per frame. That was the indoor lab demo. In the demo 3 program, we got that on a demo 2 program, on Humvees. Computers were a little faster, so we had a little higher resolution in the depth maps, a little faster. And looking down this road, we got a depth map like this, and this is the elevation map looked at from above, where bright is higher and dark is low. And we were able to drive on that. Al Kelly was a PhD student here then and spent a summer with us putting his local mapping and path planning on board, and we could autonomously drive down this dirt road at the racing speed of 2 miles an hour. And this was kind of preparatory to taking it out to Martin Marietta in Denver and integrating it onto the vehicles there. So things have come a long way since then, but there are still some hard issues. Really high dynamic range scenes are hard to deal with, so if you have dark shadows and pools of bright sunlight in the same image, that's pretty hard to deal with. And stereo is still pretty hard to make work on tall, thin grass, and that's been mentioned earlier. So some loose ends there to keep on addressing. Now, for the Army, they have to be able to operate at night. They'd like to have passive sensors so you don't have lasers and radars projecting a lot of energy out in the scene to make you more detectable. So one of the questions was, can we do 3D perception passively at night? And the obvious way to try that was with thermal infrared cameras. So the program got some mid-wave infrared cameras that's 3 to 5 microns. These were cooled. We put them on the vehicle. We tried the same thing. And this is a daytime result. Qualitatively, it works fairly well. But you need to understand the thermal phenomenology a little bit deeper. So, in thermal data, different materials heat up and cool down at different rates. So during the day, vegetation is cooler and therefore darker typically than your dirt and rock materials. And it's the other way around at night. And here's some data we took later on out in the desert, and there's some bushes out here, and they're darker than the terrain during the day and brighter the terrain at night. So we needed to see how well this is going to work. So we went out and we took data through a 24-hour period. Every 15 minutes, we took 100 stereo pairs, and then just computed the error statistics of that. There's an example of a daytime depth map and a nighttime depth map. And when we plot that across a 24-hour period, well, this is getting too deep into the details, but it worked fairly well. We didn't actually do much driving with this, but it's promising. So as long as we're working with thermal cameras, there were some other phenomenology that we ran across that was useful. And one of them was this negative obstacle detection problem. So one day about dusk, we were out in the dry river wash doing some testing, and I saw this really bright spot in the image that I thought had no business being there. And I thought, this has got to be explained. And so it turned out there was a little ditch running through here. And when I started looking into the physics of heat transport, it looked like at night these holes in the ground keep themselves a little bit warmer than the open terrain. So with the folks at SAIC, we decided to test this. They dug a trench on their property, kind of an L shape, so we could see it from all different directions as the sun went by. Took more data all around the clock, and so during the day, some of it looks darker because it was shadowed, some of it was illuminated by the sun, so it was brighter. But all night long, sure enough, that trench stayed brighter than the rest of the terrain. And we had a negative obstacle detection algorithm that used point cloud data. This was a narrow trench, pretty hard to see with just point cloud data. But if we used the thermal imagery as a cue, as we drove closer, we eventually picked it up as you might expect. So by no means a panacea, but it was a bit of progress. Now, it was well known that long wave energy propagates through atmospheric obscurance better than shortwave. So it was also a question, can we see through smoke and get passive range data through smoke with thermostereo? There were a couple of occasions where we took some data to test that with side-by-side visible cameras and thermal infrared cameras. And so here's just a couple of examples where the stereo data from the visible only sees the ground before the smoke. The thermal, maybe kind of hard to tell quickly, but thermal image sees through and we get a reasonable depth map. But we did have some errors. There was something going on, stereo matching on the smoke, and we got a patch of false alarms up here, kind of hanging out in the middle of the air. Another occasion where we did the same thing. The visible is matching now on the texture on the smoke. The thermostereo sees through, although we had the same kind of occasional false alarms here. So promising. It wasn't the focus of the program, so we didn't do anything more with that, but there are loose ends to continue to address these outliers that happen in that situation. Coming back to this vegetation issue, so Tony talked about this problem. We started out trying to, you can try to label this vegetation with color imagery that can be spoofed. We tried texture back in the mid-2000s. Texture was pretty expensive and had a pretty high error rate. So I started looking into what other sensors are there that might help this. And the first place to start was multispectral imagery spanning the visible spectrum and the near-infrared spectrum. And it was well known in the remote sensing literature that green foliage is much more reflective in the near-infrared than anywhere in the visible spectrum. And soil and dry grass starts dark and blue and gets gradually brighter toward the near-infrared. And so you could solve this problem more easily if you had a camera that could take those bands. So we took some data. There's a pond here with some green bushes in the back, and it's reflected in the pond. And we grabbed multiple bands of imagery, and this is the red band about here, and the near-infrared band about here. And all this bright stuff in the near-infrared and dark over here are the bushes. And you do a very simple function at each pixel then to label the, label the vegetation. And so everything that's green here is the vegetation and the reflection of the vegetation. So that could help us if it's green, but what if it's dry? So there's no features in this part of the spectrum that help us with that, but we looked at the remote sensing literature. And if you went out longer wavelength, well, there's some notches here due to atmospheric absorption, but some other places where there's some differences in the materials that maybe would help us. We didn't have one of those sensors at the time, and it wasn't enough priority to pursue, but that's a loose end that might someday be worth exploring, is to see whether we can use that part of the spectrum to help us with this problem. Now, Tony's already mentioned that LiDAR can help you classify vegetation. So we started working on that in the Tactical Mobile Robotics program in about 2000. And I thought my PowerPoint was set up to embed all the movies in the file, but it turned out it's not. So these are supposed to be movies. You'll have to use your mental deepfake technology to imagine this robot. If it just uses the single-axis scanning LiDAR to drive around here, it's going to interpret all that vegetation as an obstacle and just kind of drive around in here. But if you reason about the fact that the LiDAR data, some of it goes between the stalks of grass, and some of it comes back off the first stalk of grass, then the robot will drive through the grass. And then Roberto Manducci wrote a nice paper creating a simple statistical model of how far into the grass will the LiDAR penetrate, and it turns out it doesn't go very far. But if conditions are right, that robot can drive through the grass and see an obstacle, in this case a person, before running into it and go around the obstacle. And so this idea got picked up by other programs and became fairly important in this problem domain. Okay, can you do terrain classification at night passively? So the images that I've showed so far were all single channel black and white. Turns out you can get cameras that get thermal imagery in multiple wavelength bands. I don't have time to really say much about this. There's some interesting phenomenology. Main thing I want to do is just point out, in case anybody's interested in this, that DARPA had a program in the last few years called Invisible Headlights to try to do passive perception for autonomous driving at night better than has been done before. And there were data sets acquired with thermal infrared hyperspectral data, a few papers written on that. And so this data is out there now and can be used for anybody who wants to follow this up. So water body hazards, we approached this in several different ways. I've only got 2 slides left if anybody's watching the clock. this is another case where this was supposed to be a movie, but if you, and I'm just going to show one or two examples of a bunch of things that we worked on here. So if you've got a body of water that's reflecting something in the background, so there's texture on the water, then the stereo is going to match on that texture, and it's going to give you the range to the thing in the background, not the range to the surface of the water body. And you can reason about that and realize this looks like the inside of a cave. These are points way underground. There's other things you can do to help you here. And once you hypothesize a water body there, you can trace around the perimeter and figure out where that water body is, which is what you need to do to put it in a map. And now I think this movie hopefully will actually play. So we've got raw image in the middle and our depth map here. And over here we're labeling a water body that we see, and it gets put in the map and the robot drives around it. We did that with visible imagery. Same thing with thermal imagery, because thermal will also have reflections. And then lastly, Tony talked about learning for off-road driving. A big boost for that came in about 2005 when Larry Jackal created the program on learning applied to ground robotics, and kind of a framework that we espoused at the time we called learning from underfoot to the far field. Catchier names were given to this later by other people, but we were imagining that the robot has sensors for which it basically feels the ground, and then it has look-ahead sensors that it used to create a map. And then as you drive forward, you're driving over that map, and you can associate that proprioceptive data with the look-ahead data and learn to predict the roughness of the terrain a little bit further ahead. And you've probably got multiple zones. You've got a zone where you've got a Cartesian map with high-resolution data, kind of a mid-zone where your range data is sparser. We were modeling that with a polar map. And then farther ahead where you have no useful range data, and it's all based on appearance. And this is pretty much the same concept Tony was talking about earlier, where we're using the near-range data to identify the traversable ground. As we go by obstacles, we recognize those as obstacles. We can learn a model based on, in this case, I think mostly on color and simple texture measures, and predict farther ahead where the drivable ground is and where the obstacles aren't. So this was really just kind of discrete classes for terrain classification, and where I think you really want to be is a model of the resistance to motion. So you want kind of a continuous valued model of the physics so that you can figure out, or at least model the stiffness of this material and reason about that in driving through. And there's still active work on that kind of thing. So with that, I'm done. Thank you for paying attention.
My name is Jean Oh, and I was part of the RCTA program for a little over 10 years. And my talk may be a little bit different from the rest so far, so hopefully it's not too different. And this was my first project in using real robots. So I still thank Tony for giving me that opportunity. So in RCTA, the main theme over the course of many years was from tools to teammates. So we wanted to develop robots that can communicate using natural language and then perform complex missions in full autonomy. So it was a very ambitious goal, if you think now. So I'm going to talk a little bit about how we did it in back then, and then gradually move towards how we might resolve the problem now. Okay. So as you can see, the intelligence architecture was very, very complex. And by the way, this is an abstract view. So there are many more boxes within the boxes. It has a hierarchical structure. So at the top of the intelligence, there's metacognition that oversees the execution, and then underneath there's a cognitive layer that determines the steps to follow, and so on. And under that, there is a perception layer, which was composed of many perception modules. So for detecting small objects, small cars, big cars, white cars, and so on. So and then just a summary of our success was we were, even back then, were able to have the robots perform complex missions in a kind of using controlled vocabularies pretty successfully in various different environments. So the secret was for these different environments, for perception modules, we actually overfit. So we collected the data from the test ground and then retrained to make the demo work. But perception was really, really difficult then. Okay. So to summarize, what was really challenging in maybe 15 years ago was everything. So everything was really, really difficult, except maybe the planning algorithm that Tony developed, provably optimal, built this path planning algorithm. It worked great. So, but other than that, everything was failing for its own reason. So very challenging. But the highlight was the perception system. So perception is very important because based on the detection and, tracking, we're building the world model. And then the robot makes decisions based on what's in that world model. But the world model is a different world than the real world. So there were a lot of false positives, false negatives. And then so the rest in the chain couldn't really reason more intelligent behaviors. So, okay. So this is the scene that is still haunting my dream. So I've been watching this so many times. I mean, it couldn't be that difficult. It's just so easy for people. Like, what can be difficult to go just around the building to the back? But it still remained difficult for many, many years. So the actual idea that made it work was the idea called assumptive planning that Christian Libier and Tony and I all worked together, which is following how people reason. So we actually make decisions using information in the seen environment, but we also combine that with the unseen part that we fill that gap through imagination or assumption. So that completes the world. So the actual secret was ignoring the perception result. So Marshall was here, but he actually, I remember he's giving a talk on why computer vision doesn't work in robotics back then. So ignoring, so the weight on the perception results were very, very low. I didn't ignore, so there was a non-zero weight, but very low weight. But then the rest was given to the language side because there was a trust. So human commander must have given really a sensible path. So directly following the instruction, almost blindly, actually worked very well. So, okay. So this was the capstone. So in this video, what the robot is doing is actually an amazing thing. So the mission command is just screen the bag. That one sentence. It's the mission command, and which was also the capstone scenario for 10 years. So, and the mission is broken down into a set of steps, the list of steps to follow, and each step is a tactical behavior. So what the very first step is the navigation, navigating to the back of something, some important place. And then you will see a lot of kind of embarrassing results of building prediction and also bad perception, but just directly following the instruction guide the robot to the back of the building, and then also was able to detect where the exit points might be from that place, and then the robot is actually tracking human activities, and then eventually report to the commander, which was the end of a mission. So this was a fully autonomous run. So even if it looks simple, it was a lot of people, many people's work all put together over many years. So, okay. So, and then you will see someone come out the door, and then it's getting detected. So So this door detection, by the way, was a difficult problem because the way the windows look, they look the same. So the perception algorithm again had to be trained multiple times to be able to discern the differences. Okay. So that was the end of mission there. And then what we realized after these first 5 years was actually there are a lot of people in the scene. But this whole complex intelligence architecture was designed for single autonomous vehicle that's the only moving agent in the environment. So whenever we run and test at the location, if someone just passes by, that's a failed run because the robot didn't have the capability to track the moving agent and also being able to predict their behaviors. So the next 5 years focused on dynamic environment where there are people, and then also how the robot should navigate among human crowd. So, and then also different types of behavior. It's not just going straight, but depending on the mode. If it's a stealth mode, maybe it has to go in a hiding more secretly. So this was a close collaboration with the researchers at ARL. So I'm going to just skip to the next one. So this problem of using natural language to command a robot was difficult, but it's somehow still remains difficult. So many people are still working on this problem. So we use a very complex intelligence architecture, but the new generation dismisses that idea. We don't need to build intelligence architecture anymore because a lot of data and transformer will solve all of our problems. So unfortunately, the students became very lazy these days. So they're waiting for the data to come. So a lot of people tried this idea in the indoor scenario. So again, they don't want to work outside in the cold winter. So they use either simulator or some data sets that they can easily verify. And then, surprisingly, I checked the results, the leaderboard, very recently for this presentation, and they're not really doing very well. Like, the success rate is only 50 to 60%. Indoor apartment environment, like following directions. And then look at the average travel distance. It's 10 meters. That's like from here to maybe by that door. So then the robot fails. So I want to kind of see why it's still difficult. So there's a little bit of Moravec's paradox. So the highest level of intelligence, mission level, that takes the very abstract command into the steps, it seems like we have a good solution for that. So the large language model is actually very, very good at doing this, especially if we fine-tune for the target domain. This works really, really well. And then also the perception, even if it still remains difficult, a lot of problems that we encountered 15 years ago is gone almost. So the segmentation algorithm, like segment anything, it works really, really well. And then object detection also works much better. So we're happy with those progresses. And then at the lower level, we're getting better robots and better sensors and also low-level autonomy algorithms. So it's getting better and better. But the middle layer for spatial understanding turned out to be still very difficult because these foundation models don't have enough data for that part. So that leads to the grounding. So grounding means the models have great ideas, great plans, but how to ground that plan and actions into the physical environment, that still remains difficult. So this is kind of my take on how the future architecture will look like. So I think the old some good things from the old idea, like intelligence architecture, which has a modular design. I think it's coming back. And at this time, each model is a sort of an agent. So more agentic intelligence architecture. And then all the boxes will be performing better thanks to foundation model and lots of progress in AI and robotics. So this foundation model will be used for many things, vision, language, and also simulation side too, because the simulation technologies are also getting much better. So we can generate a lot of counterfactual examples, which is lacking in the real data. And then also, on top of the general data, we also want to see a lot of the real robot data, which is whatever robot we are using, we also need a little bit of that data to have a successful algorithm. So this is a maybe future direction to go. And then I actually tried ChatGPT-4, which is vision language model, to solve that going to the back of the building. And the results are very promising, except for that spatial understanding. So it has the right idea, but when it's actually trying to draw the map, it's still struggling. So, okay. So in the future, so it looks like it's very close to maybe we solve these problems, like using language for robots. But one thing that I see, still see remain challenging is dealing with humans. So the theme of the very first RCTA project was coming up with teammates, like working with humans. And we are working on robots and we are building robots for humans. But understanding humans is very, very hard. I mean, we are humans, but we don't know how to elicit our preferences. We have conflicting ideas. And it's very hard to see people making optimal decisions, so they're rational decisions. And as an individual, like if people make erroneous decisions, and as a team or a mass, sometimes we make terrible decisions too. So in this pedestrian space and also self-driving and in aviation, we see this difficulty of working with the people. So the understanding human behavior and human intent and how to coordinate with them, with the humans in the same environment may be still the challenge, and hopefully we will continue work on that. And then for RCTA, I couldn't find any team pictures. So I worked on over 10 years, but there is 0 team pictures. So I instead included my students who are continuing the work. So I'm trying to convince them to revisit this problem, and this time maybe we can do much better. Okay, thank you.